This is Unit 10 of the AP Physics C exam review. We're going to look at capacitance. So a capacitor is a device that can just store charge, right? And a common, type of capacitor is two parallel plates. Now, if you were to have a real capacitor, and it won't look like this, it'll be in like a component, and uh, you know, like it won't look like two parallel plates, but most capacitors are just made up of two sheets of like conducting material with something in between them. And we'll talk about that in a second, but capacitor, the most simple capacitor is just two parallel plates with air or a vacuum between them. So if you connect a battery to it, right, like how does it store charge? Well, if you connect a battery, uh, there's going to be a potential difference, right? That's what batteries do. Maybe it's rated at like 6 volts. So, the negative terminal is at a lower potential than the positive terminal by 6 volts. And hey, electrons, I just dropped my cap. Electrons go from low to high potential. So the electrons and, the negative charge, with the electrons, right, they're going to start moving, try to get to the other side, trying to get to the highest potential possible, right? That electrons go from low to high potential. And there's going to be a bunch of electrons. Obviously, this whole wire is, made up of atoms and electrons. And eventually what happens is the first electron, right? Let's just take a look at one electron. It heads over to this plate right here, and it stops because, you can't, it would be very hard to like jump over, the air, or, it'd be impossible to, jump over a vacuum onto the other plate. But now, hey, this plate is neutral and it has negative charges, and one of those, then that negative charge will get repelled by the negative charge on the other plate. So this electron actually repels an entire electron off, or not, I guess not really an electron, I guess just some unit of negative charge, right? It ejects negative charge off this plate, and now this negative, will go to the highest potential possible, right? And now, if you take away one negative, you're left with some amount of positive charge, right? So this process continues. More and more electrons end up, getting on this plate, and for every amount of negative charge on this plate, the left plate, that same amount of negative charge gets ejected off the other plate. So you're left with the same amount of positive charge, right? If you take away negative charge, you're left with positive charge. And then this capacitor gets fully filled up, right? Eventually, right? Like after some amount of time, if there's no resistance, and we'll talk about that in what resistance really is in Unit 11, but if there's no friction or any kind of resistance in this circuit, if you just have wires, then this thing will charge really, really quickly. And then as soon as this thing gets charged, you can actually, right, because it's storing charge, well, hey, it's also storing potential energy, right? Because the 6 volts here, by the time this thing is done charging, this whole potential is a certain amount, and that's why no more charge. Actually, yeah, let's talk about why it stops charging real quick. Eventually what happens is, why doesn't this thing charge to like infinity? Why is there not like infinite charge? Why does this process not just keep on going forever? Well, eventually the electrons are also, or the electrons, right, the negative charge, they get repelled by the negative charge on the left plate. So now they're like, oh, I don't want to go there, but I don't want to go there either, because, this is like a low potential. What ends up happening is this whole thing is at the same potential, right? Equal potential. There's no more movement of charge. So that's why it stops charging. Once it is fully charged, now there's a potential difference between them, right? This potential is at a different potential than this potential on this wire, right? Because this is hooked up to the positive side, so hooked up to the negative side. I can put like a light bulb, right? I can put like a little light bulb, which requires like electrical energy, and I can make it look like that. And now the negative charge, right, there, it's at a lower potential than here. the negatives want to go back to the positives and make everything neutral again. And by moving through this light bulb, that potential energy here initially gets converted into light. So as the negatives, as a negative meets back up with the positive, everything becomes neutral again, and you have discharge or capacitor. Now, in a circuit, and this is just to give a conceptual overview, right? If you forgot about capacitors, but in a circuit, we use this right here to represent a battery, right? One big line, one small line. You could also have, as many as you want, I guess. You usually see two of them, or like four lines. I guess maybe you could have six, I don't know. But the small always represents the negative, the big line always represents the positive, and it connects by these wires to a capacitor. And in a circuit, we used to think that positive charge was really the thing moving. So, we use, instead of electrons flowing this way, we use conventional current, which means positive charge flows the other way. And you can imagine whether negative charges are moving onto this plate or positive charges are moving the other way, your capacitor would have the same polarity, right? Like it would still have the same charges on each side, regardless of which way you think the charge, which charge is moving. So we're going to use positive. We're going to use a conventional current. Positive charge is moving. Now, we talked about how, hey, you can't get infinite charge on here because eventually the positives, right, or we talked about negatives before, we're using conventional now, positive charges that are moving, they get repelled away. So eventually you can't fit, you can't really put any more positive charges here because there's too much of a repulsive force by the positives built up there. Now, if you had a battery that was 6 volts, right? If you had a battery that was 6 volts, a voltage is also called electromotive force, right? Voltage is not force, but you could think of it as a force in the sense that it's trying to push the charge, right? This battery is trying its best to push the charge onto the plate. But once this plate is fully charged, there's not enough push force, right? It can't push any more protons, positive charge. It can't overcome the repulsive force here. So you need a bigger battery to get more voltage and to push more positive charge onto the plate. And, as soon as you get a bigger battery, then hey, you get more charge, right? Because it's able to push more positives onto the plate. So capacitance, right? The capacitance of the capacitor is its capacity to store charge for a certain voltage, right? Or mathematically, what that looks like is C is equal to Q over V. So the capacitance is the amount of charge it can store per volt, right? Per voltage provided. And if you double the voltage for a connected capacitor, well, if you double the voltage, you're not halving the capacitance because the charge also doubles. The capacitance just tells you, hey, how much can you hold, how much charge can you hold per volt? If I double the voltage, it can now hold double the charge. That's kind of the idea. So if you had something with a bigger capacitance, right, what that means is for that same voltage, right, for 12 volts, right, if I were to, I'm going to just use this polarity now, I like that better, or this battery symbol, it can hold way more charge. I don't know how to show that because this is already so packed, but oh my god, it can hold all this charge. Oh my god, it can hold so much more charge, right? Because it has a bigger capacitance, right? For the same voltage, it can hold more charge than the other capacitor because it has a bigger capacitance. Well, the question becomes, what does capacitance depend on? Because for a connected capacitor, at least, and we'll talk about examples where it's not connected, it seems like it seems like like doubling the voltage doubles the charge. So it's not, capacitance does not depend on charge and voltage. This is just the ratio, or like the relationship, right? Charge per volt. What capacitance really depends on is its physical properties. How much stuff can it really fit? You can conceptually imagine, hey, if I made these plates bigger, it can hold more charge, right? That would kind of make sense, and we're going to kind of prove that by showing that, well, if this is the definition of capacitance, right? We define capacitance by this ratio, then we just got to find, well, for parallel plate capacitor at least, I know that the voltage is the negative integral, I'll do magnitudes, who cares? The integral of the electric field times, or electric field with respect to length, right? It's that integral. And I know that the electric field, I can use Gauss's law, right, to show that the electric field for a parallel capacitor or parallel plate, two parallel plates, is the surface charge density over epsilon naught. So I know that the voltage, this is a constant, this is a constant, this doesn't change according to length. So it just ends up being the surface charge density times epsilon naught times the distance, which is the distance of separation, d, right? However far apart the capacitors spaced apart, however far apart the plates are. So if I just do C is equal to, well, Q over this whole thing, right, for voltage, well, what you notice is that, hey, surface charge density, first of all, I can move the epsilon naught to the top, right, because fractions and reciprocals. Well, surface charge density is just the total charge over area if it's uniform, right? And it will be uniform, I think. I think it'll always be uniform. There's probably some electrostatic reason why, but whatever, who cares? We don't need to worry about that. It will be ideal. So the charge crosses off and I can put the area on top. The capacitance depends on this is the capacitance for a parallel plate, right? It physically depends on its area and its distance of separation, right? To conceptually think about these, my teacher used to, I take physics too, and my teacher would say, like, hey, increasing the area, right? It gives more space, like there's more space, so that's why the capacitance goes up. That, I don't know how true that is, because in my head, well, if we're storing electrons and there's protons, those are so small. I don't think the area really makes a big deal, right? You know what I mean? Like, I don't think the area actually, I don't think the reason capacitors get charged is because it's out of physical space. But the way I like to think about it is, you could think about it like that. But also, if I increase the area, then if I increase the area, well, I know that the voltage, when it's fully charged, the voltage will remain the same. And if I increase the area, right, this surface charge density would go down, right? If I increase the area, the charge would also have to go up to balance it out. Otherwise, the surface charge density would go down. So that's why the total charge goes up for the same amount of voltage. And same thing if I increase the distance, right? If I increase the distance, well, the voltage would go down, but it has to stay the same because it's connected to this same 12-volt battery. So the charge goes down, right? The charge goes down so that everything remains balanced. So it's just balancing act, I guess, and that's why the capacitance depends on the area and the distance, because those are the things that really affect the electric field and the voltage across the actual capacitor. So that's what capacitance depends on. And you could also get crazy cases where, well, let's say this capacitor is charged, right? Now, and I disconnect it, what would happen? Actually, first let's start with if it is connected. I guess that's more simple. What am I doing? Um, if I half the distance, right? When we're changing any variables, we want to think about what happens to the capacitance, what happens to the charge, and what happens to the voltage, right? So, if I increase the distance, then the capacitance will go down, right? And the voltage will remain the same because it's hooked up to the same 12-volt battery, right? It'll always provide the same voltage. So then if my capacitance goes down according to this equation, I know my charge will go down. And then I can also think about, I'll talk about energy in a second. But, if I disconnect it, you might think, if let's say I increase the distance between the plates, right? Well, the capacitance will still go down, right? Because I know capacitance depends on the distance of separation. But will the charge go down? If the charge were to go down, where would the charge go, right? It has nowhere else to go. What would actually happen is that, the charge has to remain the same, right? So the voltage, in a kind of counterintuitive way, the voltage will actually go up, right? Because now, to store the same charge, the voltage has to be double, right? To store the same amount of charge. That's making the capacitance half as much. And if you think about it, that actually kind of makes sense because, hey, what does electric field depend on? It's just surface charge density, Q over A. That remains the same, right? The electric field between them stays the same. So if I increase the distance, yeah, the voltage would increase and my capacitance would indeed go to half. Because or not half, but I don't know why I said half. I meant just go down. If I said double the distance, then obviously we could determine that it is half. The last thing I want to talk about is energy. So if I'm discharging a capacitor, we know that charge. So the change in I know that the change in UE, electric potential energy for a charge, is Q times V. The only problem is this is for a charge going through a potential difference, right? Obviously, that's what this is. But this is like, you'd think that, this ain't this, if you start with a charge Q, right, on each plate, Q and negative Q, and hopefully we've established it has to be the same amount on each side. Then if the voltage is, let's just say the voltage was, V initial, right? There's a V initial, right? Well, eventually what would happen is, let's say half the charge discharges, right? So now you have 1/2 Q on each side. So essentially we started off with Q and now it's discharged to half. Well, now the voltage, the potential difference, is a lot lower, right? Because now the electric field has gone down, so the voltage has gone down. So it's not the same voltage. So this equation, right, just simply Q times change of V won't work. Instead, you have to think about, right, because it's not the same it's not going through the same potential difference. Well, this thing is like 1/100th, right? It won't have this, it won't, give the light bulb the same amount of energy because it's going through a much smaller potential difference. That's what I kind of mean. Hopefully that's kind of clear with how I explained it. But you're going to have, in order to figure out the total change in UE, you got to take an integral in this case, right? So dUE is equal to Q, and we're just going to say the dV is changing, right? Or should I say dQ? I guess we could do that. So for whatever charge Q, it's going to be whatever charge Q is going through a certain potential difference dV. I know that C, would then just be equal to dq over dv. So I know dv is just dq over c. I can then say, well, I can now integrate, and I can say, well, the total UE, the total energy stored, is going to be integral q over c times dq. And if I were to evaluate this antiderivative, I would get 1/2 q squared over c, right? Because it's q dq, that's q squared over c, which is a constant. So this is the energy stored in a capacitor, but it comes in, it's not just this form, because, well, what is q? Well, q over v is equal to c. Well, q is just cv, right? So if I do ue is equal to 1/2 cv squared, or c squared v squared over c, right? I get that ue, or the energy stored, is also equal to 1/2 cv squared. And what is c? Well, c is just q over v. So 1/2 q over v times v squared is going to equal the energy stored as well, or just, which is simplified, so 1/2 qv. Which is interesting, right? What this equation tells us is that the energy stored, or the energy kind of released by discharging the capacitor, is half of this equation for a constant like voltage, right? Charge continuously going through a constant voltage that doesn't change. So that's kind of interesting. So if I have I can so that's the energy. You could use this equation if you know the charge, or the voltage, or the capacitance. You could use one of these three forms to kind of figure out more information, right? This is a 12 volt battery, and I could figure out the energy stored if I know the capacitance is 35 microfarads. By the way, farads is the unit of capacitance. Capacitors generally have a low capacitance, right? If this thing was 35 farads, that is storing an obscene hundreds of coulombs. I think that's more than a lightning bolt. So that's a lot of energy and a lot of charge. Usually it's micro, like 10 to the negative 6. So 12 is on my calculator. I don't. Wait, I can get it though. I can get it. I could also check. Oh shoot, 22 minutes. I've been recording this video. Oh, I left it downstairs. Okay. You could use your calculator to figure out how much charge it has by doing q over v equals c, and then you could figure out how much energy it has using any one of these forms, right? If I've calculated the charge, I could do q squared over c, but if you're doing an MCQ and it asks what is the energy, don't use the ones with Q, right? I don't want to use the ones with Q because I don't want to have to go through the extra step of finding Q. If it's an MCQ and it just asks what is the energy stored for a 35 microfarad capacitor connected to 12 volts, I can use 1/2 CV squared, right? I know C, I know V, boom, bada bing, I can punch it in my calculator, be done with it. That is the energy equation. So, real quick, one thing I wanted to show you is, I don't know how often this shows up on the AP exam. I haven't seen it in an FRQ yet, but it is a important thing to know. Is, well, what if you had, instead of two parallel plates, what if you had coaxial cylinders, right? So if I had a cylinder, right, and it's hollow, it's it's not a solid cylinder, but let's say I had two cylinders. Actually, wait. Yeah, let's do it like that. Let's say I had a cylindrical capacitor, right? Or a spherical capacitor. Well, how can I find the capacitance? Right? How can I find the capacitance? Well, remember, the capacitance depends on physical properties. So, we can't just simply do Q over V. But let's say it does have a charge, Q, negative Q, with a voltage V. How could we find the capacitance? Well, we can do the same process we did last time. We just got to find the voltage and or take the charge divided by the voltage. Well, what is a voltage? Well, the voltage is going to equal integral EDR. And what is it? What is the electric field? Well, I can use Gauss's law. I'm looking at the voltage across this space right here, right? And Gauss's law tells us if I were to put a Gaussian cylinder in between those two, the only charge, right, the only charge being encompassed is the charge of the smaller cylinder, with the one with positive Q. So I don't have to worry about the charge or the electric field by extension of the bigger cylinder, because in between, it doesn't have an effect, right? And I think that's called Shell theorem, right? It's not, there's no electric field within this inner region caused by the bigger thing, thanks to Gauss's law. So, well, EDA is going to equal Q, and we're going to assume it's like uniformly distributed. Q enclosed over epsilon naught. For a cylinder, I can use symmetry and be like, and let's say it has a uniform linear charge density, right? So EDA, right, 2 pi RL is going to equal lambda times L over epsilon naught, where lambda is Q over the total length. And then I can divide by L, and I get E is equal to lambda over 2 pi R epsilon naught. And I can even just make sure I could even, because I know I'm going to have to hopefully cancel out that Q, I could just turn lambda back into Q over L 2 pi R epsilon naught. Right? So now I could take that integral, and I just got to be careful with the bounds. And because, I will just use the negative, so we're getting comfortable with how the negative works. Well, I'm going from R, so this is a radius RA, let's say RA, and the bigger radius is RB, like shown over here. Well, I could go from RA to RB, but I can also flip the bounds, because if I flip the bounds, that takes care of the negative. It's a calculus property. If you flip the bounds of a definite integral, the value of that integral will end up becoming negative. So if you don't know how to do that, or if you don't understand that, that's totally cool too. You could keep the negative in there. This will just help us. And I have Q over 2 pi RA, right? This is R as a this is the electric field as a function of R. My fault. 2 pi RL epsilon naught times dr. And if I pull out my constants, Q over 2 pi L epsilon naught, I get integral from RB to RA. I get an integral of dr over R. That's just ln R. And now, from fundamental theorem of calculus, I would get ln RA minus ln RB, but I can use my logarithm properties, and that will just end up being ln RA over RB, right? And now, with that, I can plug this whole thing back into here, and now I would get Q. I'm not gonna show it. It'll probably take too much time, but Q over this stuff, the Q's would cross off, and I would just end up getting 2 pi L epsilon naught over the natural log ln RA over RB. So yeah, the capacitance does indeed depend on the let me check if this is right. I'll check when I finish recording this. This is 100% right, but this seems right. I feel like I did all the steps right. So yeah, that seems right. You can do the same thing for a sphere, right? You can do the same thing for a sphere, where if this has a charge Q and this has a charge negative Q, RA, RB, For this one, I'm going to go quicker because I know that, well, for spheres, if they're shells or conducting spheres, for that spherical charge distribution, they could be treated as point charges. So I would know that the voltage across from this distance would simply be what would it be? Let me think. I'm pretty sure it would just be KQ over RB, no, over RA minus KQ over RB, because they could be treated as point charges, right? So you have the potential here minus the potential there, and then if I just divide Q over 1 over 4 pi epsilon naught, factor out the 1 over RA minus 1 over RB. For a spherical, this is spherical capacitance. I could put the 4 pi on top over, now I could do RB minus RA over the product RA-RB when I simplify the fraction, or I could just put the RA-RB on top. So I know the algebra there is probably a little quick. The main thing is just showing that, you could leave, on the AP exam, you could leave your answer like this, right? The algebra is not important. It's mainly the capacitance does indeed depend on like the radius, the length, right? Physical properties. So that's just spherical and cylindrical, what do you call it? Like capacitors. Let's just really quickly now look at some other kind of the series and parallel rules, right? So you could have a series. So you could have two capacitors in what we call in series. And the definition, we'll talk more about this in unit 11, but the definition of series is that the element, the two circuit elements are like kind of back to back, right? The wire doesn't connect anywhere else except the other capacitor, right? So these are in series. And what happens is, the same thing happens where, you have some amount of charge that ends up on this plate, and that's going to eject positive charge out of the other plate. But now, so you're left with the same amount of negative charge on that plate, but hey, where did that positive charge that got ejected go? It just goes to the other plate. The same exact amount of charge, right? Because it couldn't go anywhere else. So each capacitor in series, they have the same charge. Positive Q, negative Q, positive Q, negative Q. So, hey, that's pretty nice and neat. How will that help me, right? Why would I care? Well, let's say you were given, this was like a 6-volt battery, and you wanted to find, if this capacitor is 6 microfarads, and this is 3 microfarads, maybe let's ask, what's the total energy being stored, right? What's the total energy being stored? Well, if it was just one capacitor, it would be first of all, you might think, well, hey, you might be tempted to do 1/2 CV squared with 6 and 6, and then plus 1/2 CV squared, 3 and 6. But that won't work, right? Because now the voltage is being divided up across these two resistors. And the idea of the voltage, like the voltage across here plus the voltage across here, has to equal 6 volts, right? In order for this to be an equipotential line and that to be an equipotential line. That'll make more sense with loop rule, which once again is a unit 11 thing. But main idea is that the voltages will add up in series, right? And you could think about why, once again, in terms of potentials and stuff. But what we can do is we could say that, hey, what is an equivalent capacitor that could store the same amount of charge and energy, right? What is that equivalent capacitor? Well, to go about doing that, what we can do is we could kind of say, hey, well, I know that the voltage across 1 plus the voltage across 2 would have to equal the total voltage. And the voltage across 1, right, I know from C equals Q over V. The voltage across a capacitor is just Q over C. So I have Q over C1 plus Q over C2 equals VT. The charge is actually the same, so I can divide both sides by charge, right? If I divide by Q on both sides, I can cross off the Q, and I get 1 over C1 plus 1 over C2 is going to equal the total voltage over the total charge, right? And remember, this is not storing, this circuit is not storing 2Q, right? That's a kind of a common misconception, perhaps. It's not storing 2Q charge, it's just storing Q, because whatever Q got added here, well, this is electrically neutral, right? Like, this is the same amount of charge, and then you have the negative Q on the other side. So it's storing Q, it's not storing 2Q. Total charge over total voltage, well, that's just 1 over, like if I take the reciprocal, right, that's 1 over the effective capacitance, whatever capacitor that could store the same charge for the same voltage, that's what we call the equivalent capacitor. So you could see the reciprocal of the equivalent capacitor is the sum of the reciprocal of each individual capacitor, right? So that is kind of the series rule. So series, I will write like in sigma notation, it's going to equal, actually I don't know how they do it on the equation sheet. It's the sum of each individual, it's the sum of the reciprocal of each individual capacitor. So then what I can do is I could say, well, hey, 1 over 6 microfarads plus 1 over 3 microfarads is going to equal, well, 1 over C. I can multiply this by 2, so this is the same as 2, like both the top and bottom, it's 2 over 6. I get 3 over 6 microfarads is equal to 1 over C. A lot easier with the calculator, obviously, but then I take the reciprocal again and solve for the actual C equivalent. C equivalent is going to equal 2 microfarads. Well, what's the amount of energy being stored? Well, hey, well, actually, let's find the energy being stored. It's going to be 1/2 2 microfarads times 6 volts squared. That would end up being, if you plug in your calculator, 36 microjoules, right? How can we confirm it's really 36 microjoules? Well, let's find the voltage across each one, and then we can use our equation, 1/2 QV. To find the voltage, we know the capacitance, so we just need to know the charge. Well, if C equals QV, Q over V, then we essentially get, hey, 2 microfarads is going to equal Q over the total voltage, 6 volts. So the charge on each individual capacitor is going to equal 12 microfarads. So now I know V, right? I know V is equal to Q over C. So 12 microfarads over 6 microcoulombs. I'm so sorry, that's a unit of charge. Microcoulombs over 6 microfarads, that's 2 volts for V1. V2 is going to equal 12 microcoulombs over 3 microfarads. That's going to be 4 volts. Hey, that works out, right? 4 plus 2 is 6. Hey, physics works. And to find the total energy, I get 1/2. I can do QV now, right? That's just, I don't want to square anything, so QV is the easiest because I know the charge. So 2 volts times the charge 12 microcoulombs plus 1/2 4 volts times 12 microcoulombs. This would be 12 microjoules plus 224 microjoules, which gives us 36 microjoules. So the equivalent capacitor is just an easier way of finding the total energy or whatever you need to find, right? Now I'm going to show you the parallel rules now, and I'm not going to go through this whole example like how do you find everything, because I want to save your time. But it's a similar process, right? What am I doing? Oh, I was just thinking about what I'm going to teach after I do parallel. Maybe I'll do like a combo circuit. So for parallel circuits exist when they're each, okay, so it gets confusing. When you do combo circuits, things start getting a little crazy. A parallel circuit is when both elements are hooked up to the same potential difference, right? When both of these get fully charged, so C1, C2, so I don't know how much, they might not have the same amount of charge, right? Because charge has the choice of going either this way or that way, and it'll charge leaving the battery, it'll choose to go to whatever needs to be filled up, essentially, right? So once this gets fully charged, charge will go up here, and it'll make what's more sense when we learn Kirchhoff's laws, but that's next unit. But the voltage is going to be the same, because when this is fully charged, the potential difference here has to all be the same, and the potential along this wire has to be the same, and the potential along this wire has to be the same. Otherwise, it's like, well, how can you have a different potential here than here? So potential all has to be the same for no more charge to be moving, right? That's equilibrium. So in that case, the potential difference across each capacitor has to be the same, and it has to equal the battery voltage. So the voltage is the same. So if I do the same idea, right, and then the charge adds up to the total charge, right? Because now it's not like, oh, the ejected charge went over here. No, it's like this has a certain amount of charge that ejects a certain amount, and this has a certain amount of charge that ejects the same amount, right? So the total charge, Q1 plus Q2, has to equal Q total. And I know, well, C is equal to Q over V, so Q is just going to equal whatever the voltage is times C. So V times C1 plus V times C2 equals Q total. Divide everything by voltage, because it is the same voltage, and I get C1 plus C2 is equal to Q total over V total, which is just the equivalent capacitor, right? Whatever the equivalent capacitor is that can get the total charge for the same amount of voltage, I call it the equivalent, right? Or everyone. I don't know why I said it like that. Everyone calls it the equivalent capacitor. So for parallel, it's just a straight sum, right? Which I much prefer doing. You get happy when you see parallel capacitors. So it's equal to the sum of each individual. That's the equivalent. So yeah. Now, just to kind of show a bit of a harder example, let's say I have, how much time? Wait, let me look at how much time. I don't want to, I was at 20 minutes before. Oh boy. Okay, I'll save the harder example then. I don't want to overboard. That's a good thing to include in the Unit 11 thing anyways, is how to do a combo. So just, yeah, you'll watch Unit 11 and you'll have fun with that. What I want to do right now is talk about dielectrics. So a dielectric, if I add it into a capacitor, dielectric is just any insulating material that goes in between two parallel plates, right? And why would I ever want that? Well, that actually ends up increasing the capacitance. Here's why. If I add a dielectric to a charged capacitor, what ends up happening is the voltage across the capacitor still has to be the same, and the electric field across that capacitor has to be the same, right? Because if you want the same voltage, right, same V for the same electric, or for the same distance, right, because it's a uniform electric field, I'm not going to do the integral form. Same V for the same D, I need the same electric field. Well, hey, insulators, is it called polarizing? I forget. They kind of polarize, right? Their molecules shift. So if this is positive, 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 and then negative, 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 well, the molecules within this dielectric will shift to kind of look more like this. So it'll kind of look like that. So I get positive, negative, negative, positive, right? I just get my polarization. And this will actually create an electric field going the other way. A very small electric field that'll end up going the other way, versus the electric field that's just pointing this way. So it's kind of fighting the electric field caused by the plates themselves. So now the charge on this plate needs to go up to provide a stronger electric field to combat the kind of induced electric field, so that the net electric field remains constant. So this dielectrics increase the capacitance, and if you have a better dielectric, you can get better a better increase in your capacitance, right? Because capacitance will end up equaling kappa times epsilon I area over d, where kappa is the dielectric constant. Electric constant. So kappa, kappa, whatever. It can affect other things too, right? The electric field due to the plates will end up being the initial electric field over kappa, right? I'm not talking about the net electric field. I'm talking about the electric field due to the plates. It will go down with the initial. And if it goes down, well, your voltage will be the same. So, does the electric field change? No. That might be wrong. No. Yeah, the electric field will stay the same. Now, the charge will go up by kappa times Q initial. If I disconnect, however, I get the same thing where the Q is constant. So if I were to add a dielectric when it's disconnected and fully charged, well, the Q will stay the same, but this is where now the voltage will go down, because the electric field will then be the initial over kappa, and the voltage will then be voltage initial over kappa. But and then it's the reciprocal voltage, right? That's what capacitance is. Then we get kappa. If you have, I'm just going to do this really quickly without much explanation, because I don't know if it's really on the AP exam, but if you have a dielectric that's kind of in series like this, the effective dielectric constant will equal the sum of each one, with the same reasoning that the voltage across each individual one will add up to be the total voltage, and the charge, the induced charge, I don't really understand the charge part, to be honest, but if you had them in parallel, or if you had them in series, they add up. If you have them in parallel, it's going to be this reciprocal. So I'll get back to you maybe with better explanations as to why. But I think of it as now, well, the voltage is the same. So yeah, maybe I'll derive these in a future video. Thank you for watching. I'll go over combo capacitor circuits in another video, but this video's already gotten way too long. I did not want it to be this long. So yeah, thank you for watching.